Our next presentation is going to be, and the topic is to begin with the end in mind, data collection and DFC tracking. Our presentation is a dual presentation, I understand, with Grayson and Allison. Are you both going to come up here, or three, or okay? You're going to team. You're going to share. Well, that's cool. First of all, I'm going to introduce Grayson. Grayson, I haven't met you officially, but he is also a hydrogeologist with Collier Consulting. Allison is, many of you know Allison. She is well with Collier Consulting. Really, they've done a lot of work in my district, and we have a great relationship with them. Also, Allison, you've been engaged in GMA8, where I'm at, and I'm part of our technical committee, and we appreciate that as well. Would you give them a warm welcome on this topic? Our friends from Collier. Thank you.
Well, good afternoon. So when Grayson and I were brainstorming about this submission for consideration, I think the legislative session was already underway, and I had been asked by one of our clients to take a look at how we might approach evaluating their DFCs, because we're constantly in that planning cycle, right? DFCs meaning desired future conditions, and it's probably already been mentioned at the conference, but I have not heard anyone mention it specifically. HB 2078 that passed this session is supposed to take effect next week, and there are three highlights from my perspective regarding HB 2078 and DFCs and the ever-growing responsibilities on groundwater districts. And those are that in HB 2078, it specifies that in plain language, a district must explain how they are monitoring and tracking DFCs. In plain language, they have to describe how they have performed in achieving the DFC in the previous 5 years. And lastly, they are charged with setting interim DFC periods not to exceed 10 years in an effort to support maintaining or achieving the DFC for the long-term 50-year planning horizon.
All right, nice, Allison. Yes, my name is Grayson Dallern, hydrogeologist with Collier. And let's see if I can figure out how to move to the next slide. Success, all right. So here's just a really brief outline of what we're going to discuss today. First point, DFCs and MAGs are not connected the way you think that they are. And then we'll explain our recommendations of how to establish a groundwater monitoring network to track DFCs. And then we'll give a quick case study of how to process data for DFC evaluation. So this is just the catch you. DFCs and MAGs are not connected the way that you think that they are. So I worked at the Texas Water Development Board, the TWDB, for 5 years. I was with the groundwater modeling department, and I actually calculated MAGs, modeled available groundwater, for GMAs while I was there. So I have some experience doing it. And from my time there, what I know is that the TWDB is going to use GAMS, the groundwater availability models, which are the best available science. And they are the best available science because they are the only models that can actually cover this whole region to quantify what pumping in one district, how pumping in one district will affect water levels in another district. The TWDB is going to use those GAMS to estimate the amount of pumping that produces a DFC. But we run into a problem. DFCs, the desired future conditions, and MAGs are intimately connected. They're really married. However, MAGs, they live in two different worlds. MAGs live in this world of modeling, while DFCs never actually leave this world of field measurements, this reality. So our job now as districts is to really find where do field measurements and modeling overlap. We need to find this area. So I give a completely hypothetical example here. We're going to imagine that this pretty colored map here is your district. And As an example, we're going to say you have set an interim DFC that water levels in 2005, you actually want water levels to rise on average across this district 2 feet after 10 years. So we're going to compare 2005 to 2015, and we're just going to figure out water levels from change in water level in that time frame. So again, this map here shows in blue high water levels, and then in red low water levels. And so the TWDB, when you give them, this is our DFC, they're going to say, great, we've put in the amount of pumping, and now we're just going to average this entire area. We can do that because we have a model that covers this whole area. We're going to average this whole area, and it's going to turn into one value, which is going to be this, 139.6 feet. And so you as a district might be saying, well, great, we're going to do the same thing, but with our field measurements, with our water level data, because we know we have a lot of wells across this whole area, and they have water level measurements, so we're going to go and take all those and average them. But in reality, you have something that looks like this. You have all these wells on the left side, on the y-axis, and then if you go through time, though, where there's actually water level measurements, you see there's a lot of white space on here. The colored area is where water levels exist in time on the x-axis. Those are the years. And this means you might have one water level in a year, or you could have 100,000. It just needs one water level measurement to show up with a color. And if we look at 2005 and 2015, the red lines, the vertical red lines there are actually only 8 wells in that whole area that have water level measurements, even if it's only one, from 2005 and 2015. So we get something that looks like this, and where these wells exist, this is that area of overlap, where we have a model and then where we can actually go and measure that. If you take the water level, the average water levels in those wells for the year 2005, you come up and then you average all 8 wells together, you get 227.6 feet. The values are irrelevant for now, bear with me. Now you have to do the same thing for 2015, pretty colorful map. Average all these water levels in 2015, you get a single value of 141.7. TWDB now is able to calculate their amount of drawdown, or in this case, water level rise. You as a district say, all right, well now we need to use our 8 wells again. We get an average of 218.3 feet. Okay, so TWDB got what they wanted. They got their 2 feet of rise. They match your DFC. When you look at your water level data, though, you're like, well, we're at 9.3 feet of drawdown. This is an 11.4 foot difference, not what you would hope for. And this shows nothing about whether or not the model is wrong, or it's not saying that measured water levels and models are different. In fact, they could both be wrong, or they could both be right. Both the model and the water level measurements could be right at this point. The main difference, what I'm trying to show to you, is that what the TWDB did is something completely different than what the district did. They averaged water levels across the entire area because they had the ability to use a model to estimate water levels in an area that you cannot measure. You can't physically measure in some of these areas. And so, as a district, what can you do? This is my big point. You can either drill thousands of wells across your district, spend a lot of money and do that to figure out the water levels everywhere, or you could modify your DFCs. And this is really just modifying the way that you word your DFCs. Because we need to be able to go from this model-dependent state where the most common type of DFC is an average drawdown across a district. That's completely model-dependent. But we want to find that area where it's model and field measurement compatible. And to do that, I believe you need to become much more specific in how you define your DFCs. There are districts out there who do this with water levels from a well. I would suggest even a monitoring network would be a great idea. And you can specify a time of year. If summer, when water levels are probably lower, if that's of interest to you, you can use that time period. If winter, when you think that represents maybe a more steady state water level, you could use that. Or you could use an average across your year water level. And with that same breath, I'm going to say, you need to work collaboratively with the TWDB during the development of their GAMs. It's been said before today and or yesterday. But the TWDB, with new modeling software out there, it's now easier and or possible to actually refine these models at specific locations. If you tell the TWDB this well location is very important to me, they could refine that. They could focus on that. And now there's even local model. People who are working on local models could do the same thing for you, not just the TWDB. But right now, the way that the DFC is stated is we're asking the TWDB to develop a model that is accurate across the entire area, and it's an area that you don't actually know what's happening with the water levels in because you have no data there. But instead, you could say, hey, we know what's happening here, make the model really good here, and I believe that can happen. And then I also say you should talk to Heather Dodson at the TWDB about becoming a collaborator. She was made aware of being on this slide a little over an hour ago, so thank you, Heather, for forgiving me. But she's wonderful to talk to, and she said this is a great idea. Please talk to her, become a collaborator. That will further help to improve the models when they can get your data to incorporate more easily into their models. Transition.
Nice, thank you. So we're going to share just a few key things to possibly consider when establishing or maybe expanding a groundwater monitoring network, the physical locations of those, the spatial distribution, some criteria you might want to consider for well selection if you have the opportunity to be choosy, temporal frequency of the measurements, and some equipment that will make that much more accurate and easier. So this is a map of watersheds and 3 or several monitor wells across there. Distributing spatially within watersheds is one consideration, especially as you begin to compare water level data from multiple wells. If they are within the same watershed, it's a lot easier to compare those than across watersheds, just because of the spatial variability. The entire state of Texas has high spatial and temporal variability, but limiting your distribution to watersheds is one way to allocate resources for monitor wells. Some districts like Clearwater, Colorado County, they have management zones. So using those zones as a way to spatially distribute your monitor well locations is another approach. And some districts actually, we're talking about horizontal or spatial distribution of wells, also vertical distribution. So some districts are charged with monitoring multiple aquifers.
All right, back and forth. Okay, so the next thing to consider is your well selection. If you're going to put or develop a monitoring network, I highly recommend using existing wells. So if you're looking at existing wells to add to a monitoring network, you really want to find wells that you know a lot about. You need to be able to develop a good story for that well. So to do that, I suggest, this is my recommendation, you follow some of this. You need to know the well construction information. How deep is the well? Where is it screened? What type of casing is it using? You also need to find wells that are easy to access. If you're going to be monitoring it, if you're going to be using it for DFC analysis, you need to be able to regularly visit it. So having a good cooperator, somebody who works with you or has good access, are there roads to get to it, whatever might be the case, or can you get to it on your own? That's important to consider. Knowing how the well is utilized. You need to know if this well is being turned on and off. And if it's occasionally pumping, I suggest you even need to know how much water is coming out of that well when it does turn on. This would be good information to know to develop and put into your story. If you have wells that have borehole logging, this is also hugely important. Wells with geophysical logs or video logs. This helps you to really know what aquifer, where that water is coming from. If you don't know where that water is coming from, that water level information could be actually very meaningless. So with that same concept, I suggest finding wells that are water levels and wells that are representative of the aquifer and surrounding area, especially if you're going to do what I had suggested, where you're going to, rather than do an entire draw down across an area, if you're going to select a specific point, it's good to find a well that you think actually represents an area, considerable area surrounding it. So find wells that are screened across the entire aquifer. To do that, you probably need geophysical logging or video logs. And then I also highly recommend that you have a really good understanding of pumping activities in the area. and hydrogeologic boundaries in the area, such as sinkholes or faulting, anything that might prohibit or increase flow around that well. And another component to consider when you're collecting water level data is temporal frequency. I'm going to say the frequency of your water level measurements matters. Taking one water level measurement per year does not represent average water level conditions in that well for the year. It just doesn't. If you're going to take one water level measurement per year, it absolutely, for it to be meaningful, needs to be at the same time every year. But once you start collecting more frequent data samples, or once you start collecting water levels with higher frequency, such as 1 hour water levels, you can start to do some really cool things where you can start to look at seasonal trends and daily fluctuations, and you can start to remove some of those signals to create more accurate comparisons between time frames. And I've even seen, I haven't done this yet, but I've seen that people have been doing this. You can estimate aquifer properties in some confined aquifers with high frequency data sampling without the need of actually conducting a pumping test.
Thank you, Grayson. So some equipment that is really essential, some are useful, some are essential. Transducers are sensors, the instrument to the far left. Those sensors have diaphragms in them that respond to change in pressure. So the column of water above these sensors, the change in column of water or fluctuation of water level is what changes the tension on the diaphragms, and we can translate that to the depth of water above the sensor. So we talked about well locations and the well story. This equipment is not inexpensive, so it's quite an investment. So choosing wisely where you're going to spend these dollars is something to think about ahead of time. These pressure transducers, this is just an example of an in situ device. That transducer is $1,600. They can be deployed on a braided metal cable and retrieved each time you want to record the data, or they can be deployed on the cable that's shown on the right that communicates from the transducer to the surface at the wellhead. So it's a more expensive investment, but it saves time for monitoring, and it also ensures that the transducer is not moved in and out repeatedly, which sometimes can be problematic. So that right there is roughly an investment of $2,800. That does not include the equipment that's required to communicate with it, so to connect your computer to download the data periodically. Those accessories are an additional cost. E-line measurements are something that are always essential. So any of your field staff should always have an E-line with them. You never know when you're going to get an opportunity to collect a water level. And when you are downloading transducer data from your monitoring well network, taking those manual measurements is very, very helpful. It can help you to reconstruct some data, sometimes interpolate missing data, and also maybe correct some data. Sometimes these transducers begin to drift, they malfunction, the battery goes dead. The battery life is up to 10 years or 2 million data points for this particular transducer. So Sutton County Underground Water Conservation District was generous enough to let us look at their entire monitoring well data set. And Meredith Allen, who's here, asked me to please come up with some approach to evaluate their water level data to track their DFCs. Their DFC right now is total net drawdown is not to exceed 6 feet in 2070 as compared to 2010 aquifer levels. So before we even move forward and look at the data, the reference period that is chosen for the DFC is very important. What do we know about 2010? What kind of year was it? A wet year, a dry year? What about the years that preceded it? I already mentioned spatial variability, temporal variability. Even Deep East Texas has high variability in rainfall. They get a lot more than Sutton County, but if they get a hurricane, they could have 30% more than their long-term average. So knowing about the reference period is really important because the characteristics of that are going to propagate through your entire interpretation of your DFCs. So Sutton County has a very good rainfall network, but for this example, we're just looking at the NOAA station in San Angelo. They include Sutton County in their area. So this is the total annual rainfall across Sutton County from 2000 to 2020. The rainfall in inches is on the y-axis. So in 2010, that total annual rainfall was, I don't know, around 21 inches. 2009 was pretty nice, closer to 25. 2011 bottomed out at 10 inches, which is El Paso's average rainfall. So that variability is really important. Not that we can control it, but you gotta kind of have in mind, okay, if 2010 is my reference period, what happened before, what happened after? So, Grayson.
So if you want to actually be able to track your DFCs, you need to be able to clean your data and to do a good job of that. And the really good news, I just talked to Heather Dotson about this earlier. She made it sound like if you start collaborating with her, they'll help to clean your data for you. So maybe you can get off the hook. But either way, regardless, it's good to know your data. You have to get to know it. And to get to know it, you have to look at it usually. So you have to plot it. And once you plot it, you can start actually seeing anomalies or unexpected patterns, things you know about, you have intrinsic knowledge about that you would say, oh, this shouldn't have happened, what's happening here. So once you start plotting it, then you also need to go back to that well, the story of the well that we were talking about. Once you have a good story of this well, you can start to make corrections to water level data confidently. And we'll show a quick example of what that looks like here in a second. And then as far as other ways to clean data, using some neat tools with spectral analysis, Fourier transforms, and wavelet analysis, you can actually start to remove some tidal and atmospheric signals and even pumping signals from nearby wells. So there are some neat things you can do to clean your data. But for that example, in this case, we have raw water level data going from about 2010 to almost present, 2025, July 2025. And off the bat, you can start to identify what might be problem areas in this data. On the far left, you see this spiky behavior. It drops and then comes way up, and there's nothing that actually is the highest and the lowest water levels in that first beginning time frame. Well, going to the person who has this data, we asked them, well, what might be going on here? And they were able to tell us, oh, well, this is when we were installing equipment. This is when we were getting the well online. This is garbage data. It shouldn't even have been included. All right, good. We removed that. We don't know what's actually happening there. Moving on, we're coming in closer to the present. We see this huge upward spike in 2018. And we're able to ask the person who owned the data again, what might have happened in 2018? And they were able to tell us, oh, well, there was a huge rainfall event in 2018, and we actually see this feature in numerous wells across our district in 2018 where water levels rose. So we say, oh, wow, this is real. We're keeping this. We come a little further in time and we see this precipitous drop. And so we're able to ask again, what might have happened here? And we learn, oh, at this point we were installing a new transducer, and we learned that the reference point was set incorrectly, so now water levels are shifted far down. And then that's our bingo moment. All right, so now we know we can also make a correction here, and if you correct it, this is what you get in the red, where you're able to shift that water level up, correct it, and now it looks like a pretty decent data set.
Processing your data. So another way as you're getting to know the data is to use Excel. Most people will have Excel. You don't have to buy some fancy software. Using pivot tables and charts can be your best friend when you're dealing with very large data sets that you've never seen before, never looked at, just beginning to familiarize yourself. So Sutton County, their monitor well data set consists of 26 columns of data and 46,000 rows. So as I began to dig into their data, I was able to very quickly just create a pivot table with their data and summarize it to something that looks like this. So we have by well, by year, the average water level, and then almost simultaneously graph that. So we have depth below ground surface over here on the y-axis and well by well. So I can quickly look at the variability. There's some consistency across the district in water levels. It just is a very inexpensive, powerful tool that you can use to begin to look at the data. So for those of you who are not familiar with Sutton County, it's a couple of hours northwest of here. It might be kind of hard to see this laser on there. I'm actually having a hard time seeing it. But anyway, Interstate 10 moves from northwest to kind of the southeast through the county. Schleicher counties to the north, Crockett's to the west, Val Verde and Edwards are to the south. And these are all of the documented wells in Sutton County. So this is the district's registered well database, the SDR database, and the groundwater database from TWDB. And there are roughly 3,600 wells that I counted up just from these three data sets. So I'm going to share with you just my initial findings and just touch on a few examples. They have 31 monitor wells. The earliest was established in 1969. Some of them are just periodic manual measurements. So I filtered their entire data set to look at wells that have a pretty continuous record from 2010 to present, and that left me with roughly 20 of those monitor wells. So initially, I just looked at average water levels for each year from 2010 through 2024. So on those are the blue bars, is the average water level for each year across those 20 monitor wells that have a pretty consistent record since their reference period of 2010. And of course, this is depth, average depth below ground surface on the y-axis. And of course, year across the x-axis. And that red dotted line is their DFC. So their DFC is average water levels in 2010 plus 6 feet of drawdown. So looking across the district for these wells, it looks like in 2017 we kissed the DFC, but 2020, 2021, 2022, 2023, we exceeded the DFC. So it's intriguing, but I was not satisfied. So I decided what I'm going to share with you are just a sampling of 3 wells distributed across the district. So well 6 is up here in the northwest part of the county. Well 1335 is right in the middle of town. And then well 1000 is down here kind of in the southeast part of the district. They're all in different watersheds, as you can see from the little squiggly lines. So this graph is going to take me just a minute to describe what we're looking at here. So instead of looking at an average across 20 wells for the year, we're looking at well by well, a monthly departure from 2010. So I compared January of 2011 with January of 2010, February of 2011 with February of 2010, and so on. Because we know there is a lot of temporal variability, a yearly average or a multi-year average doesn't tell the whole story about what's going on. So that was kind of the route I chose to take. That was my next step, is let's look at this monthly departure. So on the y-axis, we have 0 in the middle. That is 2010. That is our baseline. The negative numbers indicate that the water level for that particular month was below the water level for the same month in 2010, and the reverse would be water levels that are above the zero line. The groundwater level rose, or aquifer levels were higher than the same month in 2010. The solid black line is precipitation. This is actually Sutton's precipitation data from all of their stations. So this is an amalgamation of the entire county rainfall data set. And then the DFC is 6 feet below our reference. So what you see here is the temporal pattern is quite different. So 2020 through 2023, we don't see that exceedance of the DFC. We see it earlier on, but then you'll notice this big spike in rainfall right here. That is September of 2018. That was a catastrophic flood for the town of Sonora. There were some areas that received 10 inches of rainfall in 4 hours. A lot of their monitor wells responded like this. You could see the signal in the aquifer. In many of them, some of them had no response. The wells in the southwestern part of the county did not respond. A couple of wells that are in the same watershed did not respond. So that's going to require some further investigation on my part, but you can see that flood had a very strong impact on water levels. So that tells us that the aquifer is closely connected to the surface. So rainfall variability is very important in Sutton County for aquifer levels and a number of other things too, of course. So now we're looking at that well that's in the middle of the district in town. This is well 1335. Same process, 2011 through 2025. We're looking at monthly comparisons to the same month in 2010. So our zero line is 2010. You can see that prior to that flood in September of 2018, the fluctuations were very small. You know, this is not a pumping well. There are pumping wells around it. It doesn't seem to be strongly influenced by those. But it never exceeded the DFC. It didn't even come close. This well is very interesting. So this is the one in the southeastern part of the county. This is a pumping well, which you can see from here. And I removed the precipitation so that I could add in the well hydrograph. So if we just plot all of the water level data that are recorded with their pressure transducers, because this is a curious pattern. You would expect to see for a pumping well, you have water level declines and then water level increase when the pump turns off. And you can see that very distinct pattern here. So there's nothing unusual about that. So here is the well hydrograph. And what we see is that in 2010, so I've added 2010 to this graph, whereas it wasn't in the others, the water level was uncharacteristically high in 2010 in this well. So that is our reference period, which means that all these subsequent water level measurements are going to exceed the DFC. So again, that is why that reference period is really important. It's not that it's wrong, but you got to know that when you're beginning to interpret your data. Another thing that I found really fascinating that I'm excited to look into is the change in the apparent non-pumping water level. So for the first several years, up until the flood, actually, it looked like when they shut the pump off, it generally recovered to within 10 feet of what the 2010 reference water level was. But as time marches on here, it looks like their static water level might be declining. So that's something that we want to take a closer look at for sure. So just to recap here, take good notes. When you are installing and maintaining your monitor network, take really good notes, make multiple copies. So you have your field notebook. When you get back to the office, scan that and put it in some designated place online so the people who come after you can find that, because it could be very important. and be fastidious if you are setting up or deploying pressure transducers. The timestamp on those is crucial. Ideally, they are all going to be deployed using the same laptop computer, so they are synchronized with their time. Because, for example, looking at Meredith's rainfall data and her water level data, those timestamps of when the rainstorm began, when it ended, when did we see a response in the aquifer, that information is very valuable. So time is crucial. Deployment depths also is crucial. Those transducers can be set up to measure water column above the transducer, in which case you need to know exactly where it's placed within the well. Or you can have it just read back to you depth below ground surface, in which case you still have to know the deployment depth. And always collect an E-line reading. Those have been invaluable to help interpret some unexpected patterns in these data. So that is very, very helpful and really crucial.
I'll add a little bit of my recap. Get the story of your well. You got to know the history of your well. It's critical. If you're going to be using a drawdown, a DFC with as a drawdown, your reference period is also critical. And we highly recommend, it was really briefly mentioned, so I'm going to focus on it for a second. Use some sort of long-term average rather than a specific year, as Allison highlighted. A specific year can get you into a lot of trouble. And then my favorite part is just amend your DFCs. If you want to be able to monitor how you're doing with your DFC, you have to actually specify DFC as something that you can monitor and not just something that is going to come from a model. So thank you so much. Here is our contact information. And I guess if we have time for questions, we... Okay.
I have one. You spoke about using transducers and E-lines. What about automated acoustic devices? Do you have any experience in that?
Sure. So the question is about using sonic water level indicators or acoustic that are placed at the wellhead. They do have to have a pretty clear line of sight to the surface of the water. They do not work well if the pumping or the water level at all drops below the screen. And they do not work for very shallow water levels, but yes, I have used them, yes. Yeah. Anything else? Yep.
So on your rainfall data, within what proximity do you need to have that record of rainfall? Is it at that site or?
A lot of their gauges, Meredith's right behind you. Okay, so the question that Janet asked is how close does the rain gauge need to be to the monitor well? And I think Meredith has a lot of them that are coupled. So essentially there's a rain gauge at each monitor well. That's really nice. I mean, that's best case scenario. You know, I would think I would be happy within a quarter of a mile or half a mile. The thing about our rainstorms that direction is they're convective storms, so it could rain at her location but not a quarter mile away. So as many as possible, but sometimes, I mean, there's a limit, right, to our resources. So, yes, ma'am.
Hi, Devin Harding from the Texas Water Development Board. I did just want to reiterate some of your points about the wording of DFCs, because we do evaluate them exactly as worded. And as you pointed out, you had that picture where we do the average over the whole county. If, for instance, part of your county is too deep or no one ever pumps there, that is not something you ever want to manage or monitor. Maybe don't write your DFC in a way that that area gets included, and you can be very specific. Like I said, we take your DFCs as written. So.
Thank you, Jevin.
Okay.
All right. Thank you.